Like a lot. Okay, so let's do a quick review of what we talked about last week, Thursday. What is physics? Anybody remember without looking it up in your notes? What's the point of physics? To study natural things. Nice. Whoever said that, good job. Yeah. We want to study natural things. And really the two natural things we're going to study are matter, which is really the stuff we have. Okay, matter is our stuff. This is matter. This is matter. Because it takes up volume and it weighs something. However, the flip side to matter is focus guys. The flip side to matter is if you don't do anything with it, if it just sits there the whole time and lays there, we have a very boring universe. We want to have energy to accomplish things because really energy is the ability to do work. If it can do something useful like light up a room or flip a switch or cause a circuit to run, now we have energy that's doing something. So physics is all about the stuff we have and how we get it to move and do things. Does that make sense? And so on Thursday, we talked a lot about energy in different forms, things like thermal energy, chemical energy, sound energy. Guys, focus. Are you okay? Okay, is that more important? Okay, thank you. um, Today and going forward, we're going to focus, though, just on one type of energy. Okay, the main focal point of Science 9 Energy Physics Unit is on electricity. So that's my goal today, is to give you a brief tutorial on how electricity works. And before I start with my notes, I want to show you guys a couple of demonstrations that we're going to do in our lab on Thursday. So this is a little device right here, if you guys can see. It's got two little strips of gold metal inside. I don't know if you guys can see this all that well from where we're at. But this is a super, super thin piece of gold foil. Okay. Gold is highly, highly conductive. And I've got two pieces of those right there. Now I'm putting it inside a box, and the box is going to have glass on the outside, and then inside it's going to have air. And air and glass are both insulators. So what I'm trying to create right here is a device that has both conductors and insulators. Okay, the conductors are the pieces of gold foil within the box, and then there's metal. You guys can see how there's like this little, I don't know, ball, I guess, with the metal going inside there. What we're trying to do is make it so that if I were to use some sort of electrical interaction up here, it will go inside the box, but the box is insulated otherwise. Does that make sense? Now, scientists and physicists or whoever was exploring, they knew about charges for a long time. We're going to talk about electrical charge. This is a piece of black rubber, and this is just an animal pelt. And if I were to rub this, I don't know if you guys can hear. Listen carefully. Hang on. Now, maybe you can't hear it from there. I can actually hear the little crinkliness of like hearing like it getting shocked. Has anybody ever been like shocked by your friend where you do like the and then you go up and zap them? Anybody ever done that before? I got a picture of that on the second slide here of you like getting a little bit of a zap. Anybody ever seen that before? What I've done right here is I've charged up this piece of rubber here with the pelt, and this is going to work way much better on our lab on Thursday. But you can actually see little bits of hairs on here, and they are sticking up on end, almost like when you're like your hair sticks up. Watch this. Look at the look at. Can everybody see the leaves in here? Okay, I'll hold it up. Okay, I'll hold it up. Okay, here's the two leaves there. Watch what happens when I bring it close. Can you guys see that? I wish I could hold it still. Yeah, how can we do this better? Because you guys can't see all that well from where you are, probably. Okay, so hopefully I'm holding this perfectly still. I'm going to bring this thing towards it there. Can you guys see those two leaves right there? How they're... Okay, I'll change my direction here. See that? I am not doing that with like me holding it. But those two leaves there, they are moving. See? Now, watch what happens though. I didn't actually touch. Okay, when I brought this thing close, I didn't actually touch them. Watch what happens when I actually touch this to there. Yeah, see that? They were flat down, but now they're actually up to the side. Now, watch what happens. Maybe I need to stand further back here. Watch what happens now when I touch the metal. Okay, so let me show this a few more times because maybe you can't see it from where I'm at.
That was incredible.
No, I didn't. It's very mild, this amount of stuff. Okay, so I'll stand back. Hopefully you can roughly see from where you're at. I'm going to bring the stick close. And when I do that, I didn't touch it, but I can actually make those two gold foil leaves move. Okay? Now I'm going to actually touch the little ball right here. And when I did that, let's touch it again here. See how they're actually staying kind of somewhat separated? Okay, now I'm going to touch this right here. Yeah. Well, actually, 100 years ago, 200 years ago, it kind of was. So scientists and physicists have known about they have known about electrical charges for a long time, but it wasn't until Rutherford discovered the nucleus that we could actually explain what was happening. Let me show you one more thing here. Again, because I'm doing this with like the whole group here, I don't think you can see it as well. We're doing a lab on this on Thursday, though, so you can see it better. What I've got here is on a pencil, which is made out of wood, which is a good insulator, and on plastic fishing line, which is also a good insulator, I've got a little plastic ball on the bottom, and what I've done is I've spray painted it with graphene, which is basically like a carbon type thing. And the reason why I did that is because this is an insulator, but this guy right down here is a conductor. That makes sense? So I'm trying to make it so that the ball itself can conduct electricity, but that the string and the pen do not. Now, this one doesn't work quite as well, but we'll give it a try. I'm going to bring this close. Can you guys see the hairs sticking up on this at all? Or are you too far away? Like, I can literally see the hairs sticking up on this thing here. Okay, watch what's going to happen here. Yeah, it actually was attracted to it. I'll do it again because it's so minor. I will bring the little rubber mallet close to it. I'm going to touch me just to ground it. Okay. A little bit, yeah. Yeah, it actually stuck to it. And, did you guys see that part though? It actually pushed itself away. I can actually push this. Look, I'm actually moving it away from this thing here now. I push it that way, that way. I'm not moving my top hand, by the way. Nick, you're being a little dramatic here. Okay, let me show you that one more time in case you missed that. Okay, so one more time. Let's see if they make this work here. I'll bring it close, and what we should discover should actually get attracted to this briefly. It's actually going to suck towards it. There we go, it did. See how I did that, and then it moved away? And now, if I try to bring this guy close, it actually... There we go. I hope you watched that, because that was really cool. It actually touched it, and then now, as I try to bring this thing close, it actually moves it further away. I feel like not everybody's paying attention here. This was groundbreaking, if it was 1750. So what I want to do over the next few slides is explain what we just saw there and how that was actually electricity. We just didn't know it. So is everybody ready to go through notes here? Okay, I want to do a little bit of review of some chemistry stuff before we start. Scientists have known about electrical interactions for years, but kind of like when Nick was being very dramatic there, if this happened, guys, focus please. If this happened like 200 years ago, someone would have been like, sorcery, magic, witchcraft. You can make things levitate. But like now we know about magnets and we know about electrical charge. And so it's really not as groundbreaking now, but 200 years ago it would have been. Here's the real key. It happened in 1909 when Rutherford discovered the nucleus. And if you guys recall this in our chemistry unit, this changed everything. Because before this, although scientists knew about charges and particles, they thought that the electrons were inside the particle. Okay? I want to draw a quick picture here. Thomson. Oh, that board is glitching out today. Come on. Backup board. Hang on. Let's try this one. not working? There we go. Okay. Back in Thomson's day, when they had a theory about how matter worked, it was more like this. Thomson thought there was an atom, and inside the atom were all these little negative bits. And he thought the rest of it was all this big positively charged like pudding, and inside were little raisin electron bits. And he wasn't wrong by the fact that there were electrons and positive bits, but he was wrong about where they were. Because as soon as the nucleus was discovered, we realized that all of the mass is more or less here in the nucleus, and this is where all the positive charges are. And then the electrons were around. And one of the things that hopefully you learned a bit about in my chemistry unit is something called an ion. An ion is where you either gain or lose electrons, and it causes charges. And we know that atoms are supposed to be equal numbers of positive and negative charges. Atoms are supposed to be neutral. But not everything stays neutral. Sometimes we can gain charge or lose charge. Let me go back here to this diagram right here. I don't know, you guys probably can't hear it because I'm too far away, but I can actually hear the electricity, the electrons being transferred. I'm actually taking electrons off of the fur pelt and attaching electrons to this thing right here. And if I were to do this, I might be able to zap myself. No, I can't zap myself. Let me try a different one here. I'll show you this guy. You might be able to hear this one. This is called an electrophorus. What I'm going to do is I'm going to take styrofoam, and I'm going to use the fur pelt on the styrofoam. Now, styrofoam is an insulator. So what's going to happen is all of the electrons are just going to sit on top of the styrofoam. And I'm going to put this piece of metal on top. And you might hear the zap. Did you hear that? Just a little bit there? Let me do it again. If you can't hear it, come closer, because you'll actually hear it. You're going to hear the electrons zapping from the surface of the styrofoam to this piece of metal. Listen real careful here. Okay, now, I know. Okay, now what I'm actually going to do here is I'm going to create a positive charge because I'm going to ground the electrons using my body. I'm going to now touch this piece of metal, and I'm going to actually feel it. You guys can try it later if you want, but I can actually feel the charge zapping me here as I do this. Okay, and then what I'm going to do is I'm going to lift this up, and I'm going to take my finger off. And now what I've done is my body has stolen electrons. And I'm going to put it back on top here so this thing can accumulate more electrons. I'm going to touch my finger to it. That was a lot quieter. Zap. Okay. Now watch. This thing right here should actually also be charged now. And what we should be able to see is if I bring this thing close here, it should actually cause those two leaves to move there a little bit. So this is static charge is what we've discovered. And that's what I have down at the bottom here is that items can either have more or less electrons when they're supposed to. If you have more electrons, what kind of charge do you have? Positive or negative? If you have more electrons, you have a negative charge. What happens if you have less electrons? A positive charge. Yeah. And so that's my goal today. We want to talk about how to measure and make electricity. So here's just a picture that just kind of refers to, you guys have all experienced this, I'm sure, at some point in your life. When you get zapped, you're getting zapped with static electricity. Okay? You probably heard that word before. The word static means things are not moving, and they're stationary. Now, that may seem awkward because you're saying, hang on a sec, Chris, didn't the electrons, like, zap me right here? Didn't the electrons move? And I say, okay, I agree to that. But the difference here is that they're only going to move just one time, and then they're going to stop again. Okay? The electrons were on you, and then they went to, like, say, this buzzer. So I agree they did move once, but they're not constantly moving. Because electricity is where you have a circuit where electrons are always moving. They're always going in some sort of loop. You may actually know static electricity in lightning bolts. That's actually what a lightning bolt is. It's static electricity. What happens in lightning is that you have a cloud, and inside the cloud, a whole bunch of negative electrons eventually start forming on the bottom of the cloud. Okay? So a whole bunch of negative electrons accumulate, and the ground is positively charged. And eventually what happens is all of this static electricity zaps, and it goes from the negative towards the positive. In the exact same way that if you could hear it, when I was putting my finger close to that piece of metal there, that was really like just a mini lightning bolt, where it was zapping the electrons from the metal zip, up to my finger. and I was getting like a mild electric shock. Way less, obviously, than electricity. So one of the things that scientists and physicists were able to figure out for years is a basic principle of electrochemistry, we'd call it. Like charges repel and opposite charges attract. I need to talk about this vocabulary. In chemistry or science, the word like is a little different than in everyday life. Like, for example, I like eating pizza. Okay, that's different than in physics when we talk about things that are like. If you ever hear the word like in science, it means they're the same. Has anybody ever heard that before? If things are like, it means they're the same. So if you have the same charges, they repel each other. But if you have opposite charges, they attract. And I want to use this device here again to explain how we can see that. What I'm going to do here is I'm going to charge this rod up again, negatively charged. I'm going to put a whole bunch of extra electrons on this. So this thing is now negatively charged. Okay? Now, when I bring this negatively charged thing near to this guy right here and I touch the metal, what ends up happening is now the metal is all negatively charged. Guys in the back, focus, please. The metal pieces now are both negatively charged. So this guy right here is negatively charged, and the one next to it is also negatively charged. What do negatively charged things do? Like, which are same charges, they repel each other. And that's why the two leaves, they go away from each other. Now, watch this, though. When I did this thing earlier with this guy here, I'm actually going to make this positively charged through this process. So bear with me for a second. What I'm going to do is I'm going to steal its electrons. Okay. So this is going to be me stealing its electrons. Zap, I now have the electrons. Zap, I now have its electrons. This thing had electrons, but now I have them. If I've stolen its electrons, this guy is now positively charged. Now, watch this. You guys can see this. This is now negatively charged. It was negatively charged. We'll have to do that again from the top. Can you grab that? Can you grab that styrofoam for me? Thanks, Dakota. Okay, we got to do this from the top. A little bit. I think it'll still work here. Okay. The downside is I don't have a great place for everybody to see. How can I do this better? Dakota, your textbook. Lend me a book. A couple of books here. We're going to build up a tower here. Okay, so your Rubik's Cube too. Okay, here. Now maybe it's somewhat higher. You can see it. Maybe. Okay, let's try this again from the top here. So, no, that's not the right thing. That's my pen. Okay. I'm going to add electrons to this thing here. Okay. You guys watching? Okay. This is negatively charged. I'm going to now touch this right here, and both of those leaves are now going to be negatively charged. This negative charge and this negative charge want to repel each other. Yeah. Now, watch what happens, though, when I make something that's positively charged. So, again, this thing here is called an electrophorus. I am going to negatively charge this guy up, and I'm going to put the piece of metal on top. Okay? I've gotten zapped a lot this morning. I'm kind of getting sick of it. Okay, I'm going to steal the electrons. Now, you're going to hear me electrocute myself mildly. Okay? I've now taken those electrons, and then I'm going to make sure they're mine now. I took my hand off of it again. I'm going to steal some more electrons. Okay, I'll do it one more time here. Okay, this has now lost its electrons because they're on me, and I can feel it because I've gotten a bit of a mild shock. If I bring this closer to this guy right here, anyone want to take a guess as what's going to happen to the leaves? If I have a negative charge on both of those, but this one's positive? See how they went back in? Because really what happened is that's the opposite here. Now the opposite charges attracted each other, and now these leaves came back together. So basic principle, if you have similar charges, they'll want to repel. Okay. But if you have opposite charges, they will repel it. They will attract. Opposites attract, same things repel. And we can see this. I've got a lot of diagrams here I want to show you where you guys might have been able to see this before in life. Anybody ever done the balloon trick where you like rub the balloon on your head and then stick it to the wall? What you're really doing is a very similar thing. You're taking electrons from your hair, and the electrons from your hair then going on the balloon. And so then the balloon is now negatively charged because all of the electrons came off of your head. Okay? Well, then when you stick it to the wall, the reason why it works is that the wall is positively charged, and the balloon will literally stick to the wall, which is kind of cool. This little diagram right here kind of shows you what I had with that little device there. If you have two charges that are positive, they'll go away from each other. If you have two charges that are negative, they'll go away from each other. But if one is positive, one is negative, they will actually suck in towards each other. What you can actually do is one of two things. I need you to know two words here. I'm going to skip ahead. Where is the words? There it is. Okay. What you can actually do is something either called induction or conduction. I'm going to go back up here again and demonstrate this one more time here. Conduction is where you actually conduct charge. You actually have it touch. So I'm going to charge this guy back up again. Okay. And I'm going to touch this, and if I actually touch it, I have now conducted. Does that make sense? That is one way of moving charge. I actually moved the electrons physically from here through the metal, and they're inside there. But I can actually get this thing to move without even touching, and that's called induction. And you might have heard this word used before because we can charge a lot of things through induction plates. Okay. Watch again. I'm not actually going to touch these things, though. I'm going to bring it really close without touching. So it actually hasn't touched yet. I'm bringing it close. Jesse, I'm going to start sending you guys out of here, okay? I only teach 5 days out of the year in terms of this unit. If you guys can't focus, you may as well go. Okay. One more time, because I feel like I got distracted. This is called induction. I'm not actually going to touch. I'm going to bring it super close, but I'm not actually touching. Can you guys see how the leaves were able to move a little bit? That is induction. Over my next slides, I want to explain the difference between the two things, conduction and induction. Okay. Can you guys see this photo right here? In this photo right here, what we have is a neutral object. It's got equal amounts of positives and negatives. And if I were to bring a rod that's full of electrons next to it, you know what happens is that this premise right here, where is it? Right here still applies. Like charges repel each other, opposite charges attract. Okay. Look at this picture right here. Although there's equal numbers of positives and negatives, what ends up happening is when you bring the negative guy nearby, it causes all of the electrons to get pushed to the back. Why? Well, if this guy's got electrons, these electrons right here are the same as it. It wants them as far away as possible because they repel. So the electrons get repelled. But what about the positives? What do positives like to do when they're by negatives? They become attracted. And so it ends up creating what we call a separation of charge, where what happens is although this sphere right here was supposed to be neutral, when I bring a charged object near it, it actually causes a break where all of the negatives go to the back half and all the positives go to the front half. Does that make sense? The negatives get pushed away, the positives get brought closer. Can you close that door, by the way? The middle school kids are just out for break here. Okay. That's kind of what I'm going to show on these next kind of picture slides here as well. This is that same black rod that I was using. If I were to rub this fur on the black rod, see how in this picture right here I've got all these electrons moving? Now this guy right here becomes more negative than it was before. Now it has a negative charge attached to it. Now, if you actually touch two objects together, physically touch them, it's called conduction. That's a word you need to know. But they actually have to physically contact each other. And if they touch, charge can move. Here's one object that clearly has a charge on it. And here's one that doesn't have a charge. Well, when you bring the two objects together and have them touch, well, now the charge distributes evenly over the whole items. And both objects become charged. Okay, so that is conduction. Induction, though, Induction is where you don't actually touch the two objects, though. You bring it really close. Lev. Hopefully somewhere in the back on one of the top shelves in a brown tub. Hopefully. Here, this is induction. You're going to bring an object really, really, really close, but you're not going to touch. And what happens is it separates the charges. All of these negatives right here cause the positives to come this way here and the negatives to come this way here. And that's another thing you can do. So quick summary to make sure you get the concept. What does it take to make something conduct? It actually has to touch. And charge will literally move from this item to this item. Induction is where you bring it really close, and it causes a separation of charge. I want to go back to this diagram here and try to explain what happened then. So, again, I'm not going to have this charged electron plastic rod here touch. I'm just going to bring it close. This is negative, and this right here is neutral. If I bring it really, really close, why are the two leaves still separating? And the reason why is that this top part right here is now becoming positive. This little ball up here at the top is positive because all of the positives want to come towards this guy, which is negative. Does that make sense? But where do all the negatives go? As far away as possible. If this guy here is negative, all of the electrons want to go down into the container. So I just want to do it one more time here. Recharge it back up again. Positive or negative. This guy here is going to become positive, and these two guys down here will both become negative because the electrons that are currently in this guy right here are going to try to get as far away from this as they can. And so in doing that, the electrons go inside those two little pieces of metal leaves. Now, if both of those metal leaves are negative, though, if they're both negative, they want to get away from each other. And that explains why this occurred. And that's more or less what I'm going to show you on the whole bunch of next slides that have pictures on them, is the idea of how to induce charges. So here's a picture so that you can follow this. I'm going to bring a positively charged object nearby. Is this induction or conduction? Because we didn't touch yet. Okay, here's what happens. All of the negatives are attracted towards the positives because they're opposite charged. All of the positives go to the other side. This is called that separation of charge, where the negatives come closer, the positives go further away. Well, what really happens then is if you were to ground this object, you know how like when I touched the object, what I was doing is I was grounding it. If you were to ground it, what might end up happening is to counterbalance the separation of charge, more electrons are going to come from the ground, and they're going to try to counterbalance all these positives that are right here. And if you were then to cut the ground wire and eventually get rid of this ground wire, when you eventually move this guy away, you can actually make this guy be a negatively charged object. Because what ends up happening is these electrons are coming from the ground trying to get closer to the positive rod. Right? If more electrons come from the ground towards the positive rod, and then you snip the wire, you can make this thing be negatively charged. It's called charging by induction. There's actually cell phone chargers that charge by induction these days. Here's another picture. Let's see if I can try to explain. Say you've got a negatively charged object. And again, what I'm going to do is I'm going to bring it towards a neutrally grounded object. Watch what happens. When I bring this negatively charged object really close, it again causes a separation of charge. The positives come right here, and the negatives try to go as far away as possible. And what they're going to do is they're going to go through this grounding wire and go away. Well, again, let's say that we now cut the grounding wire. All of the electrons were sent way over here. They were sent as far away as possible. You now cut the grounding wire and move this object back away. This one that's left here is now positive. It's kind of clever. So it's a nifty way to be able to make things that are charged. Okay? This is what I just showed you. I showed you a device called an electroscope. And it works on the exact same principles, only it uses two metal leaves. And then those metal leaves will hopefully push away or come together depending on charges. So again, look at these pictures here. This is induction. Say there's a positive rod right here. What happens in the positive rod? The negatives get sucked up. that make sense? And electrons can move, right? If the negatives get sucked up, then all the positives get pushed down here. But look, if both of these leaves here are positives, what does this positive and this positive want to do to each other? They want to push away. So the only way they can push away is by like going outwards a little bit. Here's the opposite. If I were to bring a negative rod towards it, which is what I did in my demonstrations, all of the electrons want to get as far away from this negative as possible. And the positives come up here. Well, if all of the electrons are down here, this is negative, this is negative, this negative, and this negative push away from each other. Does that make sense? More pictures of the same thing. I think I can move on if you guys get the concept. All of what I was just describing there, though, that's known as static electricity. Now, although I guess it's fair to say that when the lightning zaps, or when I got shocked a little bit there, yes, the electrons moved, but they moved once. They literally moved from here to there, and that was it. Okay. What we want to talk about now is electrical current, which is where electrons are going to move, but they're going to keep moving. They're going to keep going in a loop. Think of like a NASCAR racetrack. You don't just run from here to here and then stop like the 100-meter dash. You're going to go from here to here, and then you're going to loop back around and go again and again and again. That's what electricity is. That's what makes something current. And so I've got a picture here to kind of describe the same concept, only now it's got to be in a loop. Here we've got electrons, and all of these arrows here are describing electrons that are moving. And the electrons are going to move through the loop, light up a light bulb, and then come back around the other side and keep going and keep going and keep going. In order for electrical current to have like a full pathway, you need two things. You need an energy source, which is probably a battery, but you have to have a complete path. You guys can see in the second diagram here how you've unplugged it. Well, now it doesn't work anymore. And I think you guys intuitively know this because that's what like a light switch is for. It literally breaks the circuit for a little while so that the electricity stops happening. So the official name for this then is known as electrical current, but we usually call it electricity. If I were to ask you then to define what electricity is, here it is. It is the steady flow of electrons. If you can keep these electrons not just going zap once, but going in a circuit over and over and over again, that's electricity. So here's the basics of what we're going to study. When we talk about electrical current and electricity, we need at least three things. The first thing you need to have is the conductor. You also need to have an energy source. You need to have what's called a load. Those are the three requirements at the very minimum to make electricity go in a circuit. Okay. So the first part, the conductor. Normally, we're going to use wires. Normally, when I have like a circuit running around, we're going to use some sort of wires to carry the electrons. But it doesn't actually require that always. It actually can go through water or gases. I believe last week, Thursday, we talked about how electricity can actually conduct really well through water, which is why you shouldn't mix water and electricity. But normally, when we do this, it's probably going to be a wire we're going to have. So that's the first bit. You need to have a conductor. Second thing you need to have is an energy source, which 9 times out of 10 is going to be your battery. We have to have something that's providing the electrons. Okay. Now, when I did my little experiment there, I had to kind of like generate my own electrical source. I had to try to find a way to put the electrons on the styrofoam. But otherwise you're going to want to have some sort of battery. The last piece is this one here. It's called a load. Okay, and a load is a generic term we use to describe anything that uses electricity. It could be a battery, it could be a light bulb, and the light bulb gives us light. It could be a heater, because the heater gives us heat. Okay, like there's a lot of different things you could have as a load. It could be a fan, a toaster, a speaker, a light bulb. But like a load is something that then uses the electricity to do something. Okay, like for example, if you have a cell phone, the load would probably be the screen of your cell phone because it's now giving off light. Or it would also be like the microprocessors because it's now running a mini computer. Does that make sense? So 3 pieces. Something to conduct it, something to give it electricity, and then something that needs to run. Right? Like what are you trying to run with this electricity? A cell phone, a light bulb. Okay. So the last part of my lesson today now is I want to talk about how to measure electricity. If we know that electricity is about electrons running through a loop over and over and over again, how do we keep track of it? So one of the ways we measure it is known as current. Okay. We talk about electrical current. And on Thursday, we talked about this is actually the dangerous stuff. If you have too much current, it will actually either start or stop your heart. We use a defibrillator to try to get your heart going again if it stops. We also used to use, maybe they still do in Texas, the electric chair, and they do the zzz and try to put someone to death by what do you call it again? The death penalty. They would actually use electricity to stop somebody's heart. So it's actually current that's very important for this. Okay. Current is basically defined as this. Current is the rate at which your current flows. If you wanted to highlight something, highlight this. The rate at which current flows, that's what we're trying to refer to. In a way, this is kind of like a speed. Think of it as a speed. I want to go back a diagram here. Let's say that as the electrons are traveling through this loop, they are going really slow. They're going taking their sweet time. Okay, they finally got there, and then they come back around again. Okay, they're finally back to start. That would be really low current. High current means it did and back again. Does that make sense? That's what current is. It's all about how fast are they moving. The higher the speed they're moving, the faster they're going. And in a way, you got to think of it as like resistance. Okay, that's a new word I want to introduce, resistance. Imagine that you wanted to run from here to there, and there was no resistance. You could just run from here to there. You'd get there in 5 seconds, say, right? But what happens if there were a bunch of kids in the hallway? A whole bunch of the grade 6s are all in the hallway, and you have to get somewhere fast. Can you run down the hallway at full speed? Well, you might want to try, but you might not get there quite as fast because there's stuff in the way. All wires or all conductors, even if they conduct electricity, they have what's called resistance, which slows the electrons down. So the more resistance you have, the slower it travels. Does that make sense? The more resistance there is, the slower the electrons travel. And so if you want a high current, you want nothing in your way. But I mean, if you want to try to get down this hallway here at lunchtime, that's not happening anytime fast, right? Does that make sense? Because there's a lot of resistance. Okay? One of the ways that we try to solve that problem is through the wires we use. I found a picture of different gauge wires. If you've ever heard of this before, the way the gauge works is that the lower the number, the more current it can handle. If you have a 14 gauge wire, see how it's a really small wire? It's really a little baby one, right? If you have a 6 gauge wire, see how there's like a whole bunch of smaller wires put together here? The smaller the gauge, the more amps it can handle. Because basically it means that there's more path for the electrons to flow through. Does that make sense? These ones right here, there's just this one little narrow tube for electrons to go in. They could get slowed down a little bit. But what if you had this 3/0 gauge wire? Look how much bigger and thicker. There's a lot more room for the electrons to travel through, right? Use that same analogy. Imagine that this hallway here is flooded with grade 6s right before getting pizza for lunch, and you have to get from this corner down to the office. It's not that easy to, because this one narrow hallway is so crammed up with kids, there's a lot of resistance. But imagine the hallway was like really, 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 really wide. Now, I know there's still some grade 6s in the hallway, but does it matter as much anymore? If there's like a lot more width to it? No, now there's more room. That's the difference between this wire here and this wire here, is that this one can handle way more current. Does that make sense? This one can handle 20 amps of current, whereas this one here can only handle 15 amps due to the resistance. So that's current. Current is like how fast can your electrons travel through the wire you have. The other way that we measure electricity, though, is in something called voltage. So one is current, one is voltage. And voltage is a measure of how much energy the particles have. Okay? The more voltage you have, the more energy they take with them. So you could have particles that are moving really slowly around, but they're bringing lots of energy with them. Or they could be traveling really fast, but they don't have as much energy. And so we use the word voltage. It's also known as potential difference. There's a lot of vocabulary in this unit. You're going to want to make sure that you study all of the bolded words I have, because there's a ton of bolded words in this section. Voltage is known as potential difference. Basically, here's the idea. It's the difference in energy delivered between the start and end of their journey. Okay, that's like the people definition. Let me give you an example here. We talked last day about a hot wire and a neutral wire. The idea being that when you plug in a device, electrons come out of the hot wire, they then go to your toaster, they do whatever the device does. In a toaster's case, it heats it up, and then they come back again through the neutral wire. Well, the potential difference is basically how much difference is there in energy. If it started with, say, 100 joules of energy when it started, and it ended with 90 joules of energy, how much energy did it lose? I'd say 10. Because it started at 100, it went all the way through the device, and it came back again with 90. It would have a potential difference of 10. Does that make sense? But if it started at 100, and then when it came back, it only had 10 joules left, now the voltage, the difference, would be more, because it's lost its energy along the way. As it traveled through its circuit, it's lost its amount. Now, in general, all household devices usually operate on 120 volts. If you were to plug something into a socket, it's usually 120. Anybody ever though looked at like their stove or their maybe their dryer? It has like a bigger plug-in. Sometimes those ones operate on 240 volts, which means that there's more energy available because a stove or a dryer or a washer needs more energy. Here's kind of another picture to hopefully help illustrate the idea. Imagine you have a battery, and you're going to send your electrons to the loop. Right? Voltage is how much difference there is from start to finish. So if you start with 10 and end with 8, the difference would have been 2. But that's completely different than current. Current is a measure of speed. In terms of units, we measure current in something called an amp. An amp is how many coulombs move per second. And so if you have a whole bunch of these things moving around, because you have a very, very thick wire, you have more current. But they may not necessarily carry more energy or not. I have an analogy I like to use with my high school physics kids. I'll try using it with you guys too, and see if this helps make sense for the difference. Imagine in your head a water tower. Okay, just an old school water tower way up above the ground, a big tub of water. Okay. In this analogy, water is going to be electrons, and the electrons are going to start flowing in the same way that they flow in a circuit. So here's a picture of a battery. The electrons are going to flow in the battery. But imagine, for the sake of the analogy here, that the water is the electrons. Okay, and what you're going to do is you're going to put a hole. You're going to put a little hole in the water tank up here at the top. Now let's say I put a little hole in it, and water is literally dripping out, one drop at a time. That's current. Current is about how much the leak of water happens to be. So if you had a little bitty hole, that's really low current. But what if there was like a big hole and water was just gushing out? Well, then there'd be more current because of the fact that there's more water able to escape. Okay, that's current. Here's voltage. Voltage would be how high your water tower is. If the water fell, like say, what can I drop here? Let's say the water fell that far. How much energy was it able to gain in this distance right here? Well, not all that much. But what happens if I dropped it from way up there? Yeah, there's more, right? So as an analogy, the taller the water tower, the more energy it's going to have when it falls. That's voltage. But current is, well, how fast is it falling? Is it falling all at once with a massive hole in the side here? That's a lot of current. If it's just dripping drop by drop by drop, then it has low current. Does that analogy make sense? So one is about how much is able to travel. And I'd say, like, what speed is it able to travel? The second one is about, well, how much energy will it use by the time it's done? The further it falls, the more energy it has. Now, in our lab, we're going to do this on Thursday. We want to be able to measure these things. So I need you guys to be aware of 3 different devices that measure electricity. Okay. The first one is known as an ammeter. or it may also be known as a galvanometer. Again, there's so many bolded words. You're going to want to know this during this unit. An ammeter or a galvanometer. And it measures current, and current gets measured in amps. And you'll see that on one of these devices, it has a big A on it, because A is the symbol for amps. Okay, that's an ammeter. And essentially what you do is you hook up one wire here and one wire here, and it will then measure how much current there is. I'll show you this on Thursday. If you want to measure voltage, voltage is measured with something called a voltmeter. Kind of makes sense. And they look like the exact same device. They really do, except rather than there being an A on it, there will be a V on the machine instead. So one's an ammeter, one's a voltmeter. The last one I need you guys to be aware of, it's called a multimeter. And multi, meaning more than one, literally it just means it can do both. So I don't have a lot of multimeters, but they have these little dials here where it can measure both voltage and current, and often they measure other things as well. And so a multimeter measures everything. So, but usually in my lab we either use this one or we use this one, and I'll show you those on Thursday. Okay, last topic. Then I'm done for the day here. Now, of all of the stuff we've been talking about here of electricity, a lot of it was still being experimented with, and people didn't know fully what they were doing with electricity until, electricity wasn't common in households until, the 20th century, right? I mean, if you wanted to light your house 200 years ago, it would have been by candle, not by light bulb, right? Even when Thomas Edison discovered the light bulb and made that, it took a long time for us to get household electricity figured out. This is a really key year here. It was 1826. A guy named George Ohm discovered a link between voltage and current. So again, voltage is how much energy difference there is between start to finish. Current is how fast it's moving. And Ohm discovered that it was all about something called resistance. Again, I talked about resistance. Resistance is what prevents the electrons from moving. Okay. I got a picture right here that I think helps describe the relationship between the three of these things here. A volt is what gives something energy to move. Okay. And amps is what's trying to move this thing. But ohms, which is a measure of resistance, see how this ohms right here is kind of narrowing the tube? The more resistance you have, the harder it is for the electrons to move. Although the amps would love to go through here, they can't because the resistance is squishing it in. Again, go back to this picture right here. Which one of these wires would have the least resistance? Well, probably this guy, right? It has the least resistance because there's lots of room for electrons to throw through these big, massive wires. This little bitty wire down here is going to have lots of resistance. Right? In terms of my picture here, then, volts is what gives it the energy to move. Amps is the actual flow of electrons. But ohms, the resistance, tries to squish it and prevent it from traveling. Okay. We use this symbol right here. It's like it's the Greek omega symbol. Kind of looks like a horseshoe. It's the symbol we use for whenever we talk about resistance. So it's the letter omega. Okay. What I need you guys to be able to do is there's actually a formula that Ohm discovered, and here's the formula. This section is actually very math-based. So you're eventually going to want to make sure you bring a calculator or have your cell phone out because we're going to do a lot of math calculations as we go on in this unit. This is a law. It's called Ohm's law. Ohm discovered that the resistance that you have is always equal to the voltage that you have divided by your current. If you want to figure out how much resistance there is, take your voltage and divide by current. Now, you guys are doing, hopefully, you guys have done a little bit of algebra before in your math class, correct? Okay. If I give you voltage and current, you can solve for resistance, but you can rearrange this formula with algebra as well. For example, you could times both sides of the formula by current, and if you were to do that, this side here would cancel, and you'd have a new formula like I have written right here, which is that voltage is equal to current times resistance. So you may actually need to rearrange these formulas mathematically in order to solve. So there's actually three ways you can use this formula. You can either solve it for voltage, solve for current, or solve for resistance, depending on which information you have. And so I'm going to do one last example, then I'm going to call it a day. But this is something that you're especially going to need to know how to do for not only my quiz next Monday, but especially for the PAT. Okay. Does anyone still have their chemistry periodic table? If you have it, on the back of it are 4 formulas. This is one of those 4 formulas that we're going to use during the physics section. So let me try an example here. Suppose you have an electric stove hooked up to that 240 volt outlet that I mentioned. And let's say that the current flowing through it is 20 amps. My question for you is, let's figure out the resistance of the heating element. Here's how you should go about solving a problem like this. First, you got to figure out which formula you want to use. And if you literally go back to the previous page, the formula I gave you was that the resistance is equal to the voltage divided by the current. Voltage is in V. If I didn't say this earlier, by the way, the letter we use for current, we use I for current. I don't know why we don't use C. C gets used somewhere else. So this is resistance. So it's slowing it down. V is for voltage. And I is the letter we use for current. So if our goal is to find the resistance, all we have to do then is take our voltage, which was 240, and divide by our current, which is 20. So what is 240 divided by 20? 12. And the unit we use is the omega symbol here, 12 ohms. This symbol right here is called an ohm, because we named it after the guy who figured it out. For the most part, it's very straightforward. All you got to do is divide or multiply numbers by each other. But you have to figure out how to rearrange the formula properly. So if I could, I want to just try one more example that I'm just going to make up off the top of my head, and then I'll call it a class. Let's say that I gave you 20 ohms of resistance, and let's say that I gave you 8 volts. My question for you would be, can you find the current? I'm going to give you 20 ohms. I'm going to give you 8 volts. I want you to find the current. And this is where we're going to draw on your math skills, hopefully. The formula was resistance equals voltage over current. Here's the problem, though. This formula is currently set up to find me resistance, not current. So I have to rearrange the formula mathematically and get I by itself. So I need to do a quick tutorial because I don't teach you guys math. Have you guys ever heard the term cross multiply? Is that something that's come up before in math? Okay, here's what you really need to do. You need to cross multiply this current up here to the other side. We're going to take current off the bottom of the right-hand side and put it on the top of the left-hand side over here. However, now current is not by itself anymore. It's next to the resistance. So I'm going to divide both sides by resistance and make a new formula. Current is your voltage divided by your resistance. Should I do that again? Okay. So the formula, different color here. The formula that we're given is resistance is voltage over current. Here's the problem. I don't have current by itself. I'm trying to solve for I, but I need to have I equals something. So mathematically, we need to know how to get I rearranged with algebra. So one of the things you have to do is cross multiply. And if you guys know this skill, essentially what I'm going to do is I'm going to times both sides by I, and this basically comes up to that side over there. Is that a skill you guys are familiar with in math? Yes. Cross multiplying? Okay, I hope so, because you definitely need math skills for this. The second part of this, though, is that now that current is being times by resistance, we have to get rid of R for resistance. And to do that, divide both sides by R. So long story short, all of this is to tell you I have a new formula here. Current is voltage over resistance. Now, if in math that's something that you're good at, that's great. But if not, I've got a cheat sheet on here for you. Go back a previous slide here. I found this slide here so that it has all the formulas for you. So if you're not very good at doing the rearranging, figure out which formula we need. We were looking for current, I believe. So here's the formula that has current by itself. And so what I might recommend to do is write these down on your formula sheet. So the one that's given to you is this one right here, but there's two other ones you might need. So now that I've rearranged it, though, now it's really easy. All I've got to do is take my voltage, which was 8 volts, and divide by my resistance, which was 20. So all I got to do is take 8 and divide by 20. Anybody have a calculator? What's 8 divided by 20? Okay, so then the final answer is this will be 0.4 amps. This is the thing that I imagine is going to throw most kids off the most, because this is where physics really begins. Physics is very math-based. You have to have some really good math skills. And because I'm not the one who also teaches you math, if this was a struggle for you, can you please call me over and I'll try to give you more of a tutorial on how to do this? If you felt comfortable with that and you're like, no, I get this, that's great. But if you were lost there, I can try to work with you guys on some of the math behind this, okay? So I'm done my lesson now. That's all I've got for the day. 2 last pieces of advice. Okay? Piece of advice number 1. There are 10 minutes left. I would strongly recommend try a couple of questions in your assignment. Okay? If you have your assignment in front of you, let me walk you through a couple of questions that you should be able to do now. For example, question number 10 is about what I talked about a little bit earlier. It said, describe the purpose for voltmeters, ammeters, galvanometers, and multimeters. That's something that we just talked about. Why don't you do it right now while it's fresh in your mind? Question number 11, if you have it in front of you, says, use the water tower analogy to explain the difference between current and voltage. Again, I just did that a few minutes ago. Maybe do it right now while you remember it. Or question number 12. Number 12 is what I was just working on now with some of these math formulas. I'm going to give you a couple of numbers, and you have to use the formulas given to try to solve for the remaining value. So if you could, I would use the last 10 minutes here and give some of these a try. Okay, that's number 1. Number 2 piece of advice. Rewatch my video. Okay? Because I know some of you guys weren't giving me your best attention today, but you can go back and rewatch the lesson, okay? And I think that's really important to do because tomorrow I got to move on. Okay, so tomorrow we're moving on to more stuff. Okay, so I'll stop now. You guys have about 10 minutes left. Make sure you guys come ready for class tomorrow, by the way, with printing done. You should be able to do basically from numbers 1 to 12, yeah. Okay, so I don't expect you to do them all right now, but do a little every day. Does that make sense? Okay, I'll stop. You guys are free to do what you need to.